Okay, hello everyone. My name is Daniel Penangian, and today I'm going to present our work, Real GDSR, Real Guided DSM Super Resolution via Edge Enhancing Residual Network. So this is a joint collaboration with Sanya Bittner under her group AI for Building Modeling at the German Aerospace Center, or DLR. So to get the same understanding of what a DSM is, a digital surface model is a digital representation of the art of topography, including all the objects in it, like buildings, vegetations, or some street objects. And one of the ways to get this data is using satellite. One of the examples you can see on the right-hand side of the slide, which coming from World 3.1. But there's also another example, like this spaceborne mission StarToSat-1, which provide global coverage, but lack the finest level of resolution, which sometimes in different applications will be very important, like urban reconstruction, for example. And to improve the resolution, meaning that technically we have to improve the measurement equipment, but it is a difficult cost and also time consuming. So in deep learning, there's a task called image resolution, where it's exactly enhancing the resolution of an image from low to high. And here at DSM, we can see it as a depth image, where the pixel values denote elevations instead of distance to the camera. And there are already so many approaches, but here I write down four, probably the most important ones, starting from a basic bicubic, which is using interpolations and to estimate your pixel values, and non-local means, which averaging similar patches across the image, to the smoothing over the bicubic upsampled image, and some deep learning based model like CNN, one of the first ones, which like another deep learning model trying to learn the mapping between the low resolution and high resolution images. And one of the latest, probably it's not so new because it's already a long time ago, but it's kind of state of the art right now, is using an advanced deep learning model which requires two different subnetworks. First, a generator which tries to generate an image, and second, a discriminator to sort of say that this image is fake or not, and they're competing with each other to generate these images that perceptually closer to the ground truth. So in DSM domain, or the digital elevation model domain, we can see that these approaches also are applied. In 2015, non-local means used for this. This is here RNN, which is using CNN, and also the GAN-based method. But yeah, there are some limitations of the previous approaches. That first, it is mostly done for DTMs instead of DSMs. And second, that normally train on bicubic downsampled samples. So coming to the challenges, then based on these two different characteristics, we try to ask if we can design a super resolution framework which is constructing on detailed and smooth DSMs. And second, how to design one that also accept real low resolution DSMs as input. As you can see in the examples below, that real low resolution ones normally doesn't preserve so much information as the bicubic downsample, which is normally used now for training. So our idea is to use another or a different modality for the same urban areas as an additional information and to add it as a guidance in the learning process. In this case, we use the optical image of an area to super resolve the low resolution DSMs. And we also try to we also try to highlight some kind of divide the problem into simpler steps. First, it's focusing on the local features, and the second, the global features. So as you can see in the figure, we have as an input this low resolution DSMs. We first assemble it with bicubic, and then we do like we already mentioned in the previous presentations, we do an early fusions where I concatenate the DSMs and also the optical image, the guidance. And then we extract some features from it, and we apply these two different steps, which is refinement and diffusion, which I will explain in the next slides. So first, for the refinement network, it is consisted of shallow CNN network. So the idea is coming from the DSMs, different than the RGB images. It has a lower information to work on, and we want to make the model as efficient as possible, so we make it shallow with a small receptive fields, which also make it to highlight only local neighborhood based on one pixel. And second, we want to have it residual, meaning that we want to predict the height difference rather than the absolute. So with this kind of input, low resolution 1, we get some output like this using the refinement network. And this is further enhanced by the diffusion loop network, which is a hybrid diffusion. It is actually inspired by work already done by the people from the ETH, if I'm not mistaken. Which is using hybrid diffusion. It's basically anisotropic diffusion, but instead of getting the guide from the actual input, it's using the features of a guide or additional information. In this case, it's optical image. And it's using the features which is extracted from pre-trained deep learning models like Backbone, like ClarisNet, or other models. And it has an edge enhancing characteristics, which means that it preserves sharp edges from guide, which at the end, as we can see in this example, with interval 0, it's actually okay. Now it's doing these multiple iterations and trying to diffuse the pixel values to make it smooth, but still preserving the edges. So the details in the experiment is as follows. We try to first apply 10 times resolution, which means from DSMs with 5 meter GSD, we want to make it to 0.5, and we work with real samples. This randomly sampled area in Swiss cities, Zurich and Bern, with the resolution from Cartosat-1 mission, which is from satellite, and the ground truth or the high resolution DSMs from Swiss government portal, which is aerial. And we're using 2,200 patches of 256 times 256 pixel, and we're focusing on urban areas using SD global line cover map. And for the training, we use ResNet50 feature structure, and we train the models in end-to-end manner using L1 loss and perceptual loss for the refinement. So how it performs? Our method outperforms the other models. So first we can see from the RMSEs, the final model actually has the best RMSE, while the model with diffusion has the highest or the lowest is one or the best, and MAD and median absolute error. And we can see from the qualitative evaluation that our methods also keep reconstruct the building shape accurately, and also has no noise at all if you compare it to the DSR again, and also construct the height distribution pretty efficient. In another example, we can also see that the height discontinuation is actually preserved. Yeah. So as a conclusion, we prove that shallow CNN and hybrid diffusion is actually sufficient for DSMs, and we do it by using local refinement and edge enhancing diffusion, which restores this substantial geometry and smooth height discontinuities. But as seen from our experiment, we see there's still a trade-off between bias and variance. So in the future, we know that now we're training only relatively small samples. We want to make it better by using bigger and also more diverse training data for generalization. And second, maybe we also can try to separate the training steps. So one for the refinement and the other from diffusion loop. And the third one is that we know that this high resolution optical image is not so available for many areas. We can try to use more available one like the Sentinel-2 as guidance. So thank you so much for listening. If you have any questions, I will be happy to answer.